Welcome to This Explainer. Today, we're diving into the fascinating world of special-purpose diodes and uncovering the hidden hardware that literally powers our entire modern world. If you think you know what a diode does, well, prepare to have your perspective totally shifted.
It's a great question, right? We usually think of a diode as a basic, one-way valve for electricity. But standard rectification is really just the beginning. Today, we'll discover how tweaking atomic structures and altering the physical geometry of these components unlocks some truly mind-bending technological capabilities.
To make sense of all this, we're going to break it down into 5 quick parts. Beyond the standard rectifier, power and high-speed switching, microwave and RF components, optoelectronics, and finally, mastering the semiconductor junction. Let's jump right in. Starting with Part 1, Beyond the Standard Rectifier. Think of the standard PN junction as your baseline. By manipulating doping levels, swapping out junction materials, and altering the physical geometry, that basic one-way flow is completely transformed. It's kind of like taking a standard bicycle and engineering it into a race car or a submarine just by swapping out a few parts. We turn a simple current flow into an instrument of precise control over light, microwaves, and voltage. Moving on to Part 2, Power and High-Speed Switching. Meet the heavy hitters and speedsters of the diode world. First up is the Zener diode. Its superpower, rock-solid voltage regulation. Unlike a normal diode that would just fry under too much reverse voltage, the Zener is literally designed to thrive right in that reverse breakdown region. Once it hits that specific breakdown point, the voltage stays perfectly constant, even if the current is jumping all over the place. When you actually wire it up, the Zener acts as a dynamic shield. As the input voltage fluctuates wildly, the Zener just adjusts its own current draw to absorb those shocks. It keeps the output voltage perfectly stable. It is basically the ultimate electronic shock absorber. Next, we have the speed demon of the group, the Schottky diode. Instead of joining 2 semiconductors together, it uses a metal semiconductor junction, usually aluminum paired with N-type silicon. This gives it a super low cut-in voltage of about 0.3 volts. But its real claim to fame? It's blistering speed. To really appreciate that speed, we gotta talk about something called storage delay. This is a pesky bottleneck in standard diodes that really drags down processing speeds. See, when you try to switch a standard diode from on to off, there's a lag because all the minority carriers stored right at the junction have to be cleared out first. Think of standard diodes like a toll booth with massive traffic backups. Those stored carriers are just cars waiting to cross. But the Schottky diode? It operates entirely on majority carriers. It acts exactly like a wide-open highway where electrons merge instantly. The result is zero storage delay, which is absolutely crucial for modern, high-speed digital circuits. All right, Part 3, Microwave and RF Components. Welcome to the realm of the quantum weirdos. Take the tunnel diode. By heavily doping the semiconductor, engineers create an ultra-thin barrier, so thin that electrons actually quantum tunnel right through it. This creates a bizarre anomaly called negative resistance. Pushing more voltage into the diode actually makes the current decrease. This wild property makes it a perfect high-speed quantum oscillator. Then there is the varactor diode, which essentially moonlights as a voltage-controlled capacitor. In a reverse bias junction, the P and N regions act like metal plates, and the depletion region in the middle is the dielectric. The genius here is that by just tweaking the reverse voltage, we physically alter the width of that depletion region. This dynamically changes the capacitance, letting us electronically fine-tune radio receivers with 0 moving parts. Next up, the PIN diode. It literally sandwiches an intrinsic or super lightly doped layer right between the P and N regions. In a specific reverse bias condition called the swept-out state, high-frequency microwave signals pass straight through without any loss. Switch it, and that intrinsic layer suddenly becomes a massive roadblock. This makes it a highly effective, incredibly fast passive microwave switch. Moving to Part 4, Optoelectronics. Let's see how these junctions translate light. A photodiode is designed to run in reverse bias. When photons hit the junction, they physically smash atomic bonds, generating whole electron pairs. The internal electric field sweeps them apart, creating a current. What's so beautiful about this is that the reverse current is directly proportional to the light intensity. It literally translates light levels directly into a precise, readable electrical signal. For extreme sensitivity, we use the avalanche photodiode. It runs in reverse breakdown.
The strong electric field accelerates a single photon-generated electron so incredibly fast that it crashes into other atoms, knocking their electrons loose, which then knock more loose. It's a multiplier. One single incident photon triggers a massive exponential cascade of electrons.
Now, you might be wondering, how is this any different from a standard solar cell? Well, a photodiode needs an external battery to provide reverse bias just so it can sense light changes. A solar cell, on the other hand, operates without any reverse bias at all. The illuminated junction itself acts as the battery, actually generating its own power entirely from that light. And performing the exact inverse function of a photodiode, we have the LED, the light-emitting diode. Instead of reverse bias, it's forward biased. Electrons and holes are pushed into the depletion region, and as they recombine, they release their excess energy as pure, visible light. It's translating electrical current back out into the physical world as a photon. The really cool part is when we combine these light-translating components into something like an optoisolator. It packs an LED and a photodiode into the exact same tiny package, separated by a physical air gap. The input circuit turns the signal into light, which shoots right across the gap, and the photodiode instantly converts it back. It's a light bridge that perfectly transmits data while keeping sensitive low-voltage systems completely galvanically isolated from dangerous high-voltage circuits. Finally, Part 5, Mastering the Semiconductor Junction. Let's step back and tie this whole fascinating taxonomy together. Think about the pure elegance of semiconductor physics here. You have three devices interacting with light. Just by changing the operating bias state, reverse bias for sensing, zero bias for generating, and forward bias for emitting, you completely redefine the component's primary energy translation role. Looking at this whole field of special-purpose diodes, it's amazing how each one brings its own unique superpower to the table. Whether it's the Zener managing voltage, the Schottky enabling zero-delay computer switching, or the Varactor tuning your radio, every single one of these miraculous capabilities comes from cleverly manipulating that one core concept, the p-n junction. So I'll leave you with this thought. Standard one-way electricity is really just the starting line. By mastering the microscopic landscape of the semiconductor junction, engineers haven't just created a few neat components. They have built the invisible, high-speed, light-driven backbone of our entire modern world. The next time you stream a video or adjust a smart light, ask yourself, how many billions of these quantum-level superpowers are firing at this exact second just to make it happen? Thanks for joining me for this explainer, and keep exploring.